Is it working? There we go. All right, welcome back to, there's an echo. Hold on one second. Okay. Okay, great. Welcome back to the live stream. I had the Google form that you all submitted your questions on, and I came up with a list of things that you all asked that are great chemistry, but just not on the Regents exam. And these are all of the things that I won't be addressing because you will not see it on Tuesday. Somebody asked about molecular and empirical formulas and finding them based on percent composition. You will not need to know that. You do need to know what an empirical formula is and a molecular formula and how the two are related, but not actually have to calculate them based on percent composition. The next thing was molality. That again is another unit of concentration in solutions that some chemistry teachers do teach. It is important in AP biology and biology just in general. It is really good chemistry, but again, not on the Regents exam, so we're not talking about it. Continuous spectrum, I'm not 100% positive what that is, but I consider never really heard about it. I'm not going there because I can tell you the story of spectra and how it's produced in an atom, but nothing about continuous spectrum. One of the big things that's not on the Regents exam, which is a shame, is SPDF configuration, writing and drawing orbitals. Not on that on the Regents exam. Any organic compounds you cannot use table P, Q, or R for. So that would be like your benzene rings and all those other things, not on the Regents exam, so we're not touching them with the 10-foot pole. Graham's law, which is about effusion, nothing about that. Something else that I don't have on here, but is still not on the Regents exam, was partial pressure, which showed up. And that particular one, we're not touching with, again, with the 10-foot pole. Math using Avogadro's law, we're not talking about that. Naming acids and oxyacids, not talking about that. Reducing and oxidizing agents and factors, not on the Regents exam. Equations that are not from your reference table, so again, molality and things like that, not on the reference table. Calculating voltage and voltage potential, and the word stoichiometry itself, not on the Regents exam. So I'm going to apologize in advance because I don't have a PowerPoint set up. The PowerPoint, I don't have one because it's kind of off the cuff. If you have any questions, feel free to text in any of your questions. I have my cell phone here as well as the sidebar that I'm watching you all right now. Sending messages. If there's something that you want me to address, write it on the sidebar or text in through Remind. So to text in through Remind, you're going to text number 8101 and you're going to put in @livechem with your name and anything you want to send in, just send it. Okay, other things that came up that are in, that was on the list of things to address was vapor pressure and using table H. I addressed that in the live stream on phases, so go back and watch that. I wouldn't do that again, only because I do the same thing all over again, and it's not worth the, the time that we have together. Somebody asked, I think it was Danny McDonald, he wanted to know the Regents curve and how bad it is. Historically speaking, the Regents curve stinks. It's awful. It's bad. Usually about 50 points is passing. That's not the way it always is. Sometimes it can be as low as 47, 48. You don't want a 47, 48 point test for passing because that means the test was actually harder. At the same time, I've seen it go as high as 52 or 53 points out of 85. And you would be like, okay, awesome, because it's easier to pass, because it's, no, I messed that up. You don't want a 52, 53 point test because you need more points to pass, but at the same time, they make it like that because the exam is actually a little bit easier. You don't want either of those. So usually 50 points is passing, and that's kind of what you want. The negative curve can start anywhere by about 75%, can go all the way up to about 80% where the negative curve starts. So basically, the chemistry Regents exam, the curve stinks. So with that being said, there are some things that I want to address with you tonight that you sent things in, and this was kind of, I guess, the game plan of where we're going over the next, time that we have together. One of the things that I was supposed to address in the hour that I had was phases and phase changes, and one of the things I didn't fully get to do with you was gas law, so I'm going to go back and do a little bit of gas laws with some kinetic molecular theory in there. One of the things that you all texted in or you Google formed in was elements, compounds, and mixtures, how to separate them, some allotropes, so we can touch base on that. Somebody texted in, not texted, somebody Google formed in later on something about energy and talking about the different properties of the different forms of energy. I mean, I can mention them and discuss them briefly, but you're not going to be as specific properties. The next thing that was kind of big was compounds and formula writing, because that video wasn't there. So we'll go over some compounds, formula writings, how to know when to name things appropriately, shapes and intermolecular forces. I can hit sig figs. Le Chatelier and redox, I can do my best to get them in as well, but we'll see how much we can get in. So let's start with gas laws. So really quick, for those of you that didn't tune in or need to have a quick refresher, there is the idea of the ideal gas law, which describes the behavior of gases. So if you have an ideal gas, the conditions that would make this an ideal gas would be high temperature and low pressure. And if you think about what this means, well, a gas would want to have a high temperature so it can spread out more, and it wants to have a low pressure so it's not confined. And as you do this, you want to compare this to real gases. So if you have a real gas, you want a low temperature and a higher pressure because it makes it behave more real life. And the way I explained this in the other video was the vacation theory. And if you think about it, you're going to be on summer vacation in about a week, and the temperature is going to be super high, the pressure is going to be super low because the Regents exam is over. And that's pretty much what it's going to be like when you're sitting on the beach in about a week because you're on summer vacation. So here, now on this side over here, when you talk about real gases, this is more like real life, and I think of like midterm week where the temperature is low and the pressure is high because you're taking midterms, your juniors, your sophomores, high stress years, and the temperature is super low. So okay, the next thing, I'm just looking at the stream really quick on the side. I can do a catalyst thing for you. I can do the activation energies. I'm looking at allotropes. I'm going to get to all of that. I wasn't planning on doing the catalyst and reverse reactions, but I can do my best to see if I can get there. So back to the ideal gases and real gases. Okay, in order for you to have an ideal gas, a gas is going to move in constant, random, straight line motion. And the reason why it is constant, random, and straight line is because they have very weak forces of physical attractions for each other. Now, at the same time, you also want to have a gas particle that's really, really small or have a low mass because it needs to float, and well, gases float, and that's what they do, and that would be pretty ideal. So the examples of an ideal gas would be something like H2 or He because they are super small and they have weak forces of physical attraction. H2 is nonpolar, so he's not attracted to things, as well as He. He's a noble gas, and he's like, I am too noble to play chemistry with people because my valence is full. At the same time, a real gas is going to have curved motion or curved patterns because there are forces of attraction. So physical attraction occurs between the different molecules, and they are usually heavier, which means that they behave more real in life than they would ideal. This is just the idea that, you know, gases have behavior. In order to make a gas behave most like a gas, you want these conditions. So on this side over here, ideal, over here, real. I want to tie this really quick into something that somebody asked, which was the kinetic molecular theory. Now, the kinetic molecular theory is the idea that all things are in constant motion. And if you just look at the name, the word kinetic means movement. So things are constantly moving. Molecular means like really tiny things like molecules and atoms, ions, all that jazz. And the theory is that it's an idea because no one has actually really seen it. We have all this evidence to suggest it, but no one's actually ever like witnessed this firsthand because nobody's ever seen an atom or a molecule because they're just too small. The kinetic molecular theory explains why solids are solids. It explains why liquids are liquids. It explains why gases are gases. And an offshoot of the kinetic molecular theory is the ideal gas theory. So that's the deal with the gas laws, that's a lie, with ideal versus real, and the idea with kinetic molecular theory. Now, moving on. Okay, one of the things that popped up was Charles' law, and Boyle's law, and Sachs' law. I'm like naming them all. Somebody said something about Pivner. We're not doing any of that. In terms of what you need to know for the Regents curriculum, you need to know the combined gas law. And you are going to find the combined gas law on the back page of your reference table, which my daughter actually stole the reference table and was playing with it because that's what my 2.5-year-old does for fun. I don't know where it went. And I might have to print another one. But the combined gas law looks like this. P1, V1, T1, P2, V2, T2. So just checking the feed really quick. It says, can we go over what the structure, molecular, empirical are, what they are? Sure. Hold that thought, Tyra. Okay. Oh, no, not the reference table. Damn it. Where are the reference table go? Give me 30 seconds. I think hold on. Don't go anywhere. Greg, is there a feed to the reference table underneath the chair? I found it. Okay, so you're absolutely right, Newt, $10. It was drawn on by my 2.5-year-old, who's an absolute animal. And the really scary part is that she drew on it, and I remember seeing it, and now the back page is gone. So with that being said, I pretty much know all the equations on the back of the reference table anyway. So we're all good, but the idea here is that you will find this equation on the back page of your reference table, which is called the combined gas law. Now, what you need to remember, color-coded markers, with your combined gas law is that you are comparing two different sets of conditions for the same gas equation. Oh, no. Hold on. What did I do? Okay, good. I took the volume off. So this would be condition set number 1, and you are comparing it to condition set number 2. You're comparing the same gas at 2 different conditions. So actually, why color code the same color? Because these are 2 completely different ideas. So you are comparing the same gas at 2 different sets of conditions. Now, what you need to remember here with the combined gas law is that you have to keep your units consistent. So if you are going to have pressure, you better have the same unit of pressure on the other side. If you're talking about volume, you better have the same unit of volume on the other side. The same thing with temperature. Now you can use for pressure, we're gonna write this over here, pressure can be in atmospheres. Pressure can be in kPa, kilopascals. Now, if your chemistry teachers like me, they might also teach you these things like torr, or they might teach you these things of millimeter of mercury, which are fantastic chemistry, but they're not on the Regents exam, so we are not talking about those 2 today. Somebody just said, could we also go over percent abundance? Sure, that is not parts per million, and you're right, I should never leave my 2-year-old in charge of my reference table. You're right, I'm a horrible mom. Okay, so when we talk volume, okay, volume can either be in milliliters or liters, it doesn't matter, but they do need to be consistent across the board. The one thing you do need to remember about temperature is that temperature must be in Kelvin. You can never, ever use Celsius like ever. That is what Taylor Swift was singing about in her most recent song, We Are Never, Ever, Ever Getting Back Together. She was really like, you can never, ever use Celsius ever. You can't do it. You have to convert into Kelvin. And the reason why is that in Celsius, you have a 0 degree and you have a negative sign in the scale, which means you are going to end up messing this up. You cannot divide by a 0, which that just doesn't work in math. You're going to get an undefined, and well, if it's negative, you're not able to do that. So you have to use Kelvin in order to do this. You can never, ever use Celsius. We're not hurting its feelings. I promise you, Celsius has a lot of other applications out there, but you have to use Kelvin in this equation because of the 0 right smack in the middle of the scale, or Fahrenheit. You're right. Somebody just said you can't use Fahrenheit either, but you can't use Celsius because of the 0 right smack in the middle of the scale and the negative sign. So this is the idea with the combined gas law. The really cool thing about the combined gas law is if they give you math problems, they can say things to you like, okay, so you're going to use this formula, and the idea is that you are going to have an initial set of conditions. the pressure is like 1 atmosphere, the volume is like 50 milliliters, and the temperature is being held constant. Okay, so they're going to say, okay, well, all of a sudden the gas is changing, and now the pressure is now, I don't know, 2.5 atmospheres. The volume is now 20, no, just kidding, is X because we're solving for it, and the temperature is being held constant. If something is being held constant, what you can do, yes, I did mean V2, thank you. If the temperature is being held constant, you can cross off your temperatures and just use the equation in order to just plug it in. Now, you would just put in your information. So this would be like pressure 1 is 1 atmosphere, volume is 50 milliliters, then your pressure 2 is 2.5, solve for X, it's algebra. We're not going to go over that. You solve for X, don't really do it. We're just going to move on. Now, the other thing that can happen here is that they don't have to give you this information exactly. They might be super sneaky with you, and they might say to you, okay, they might say to you, you have a gas at STP. This is the initial conditions. So P1, V1, T1, P2, V2, T2. You have a gas at STP, which are the initial conditions. So this means standard temperature and pressure. Now, if you go to your reference table, and you go to reference table A, and you take a peek, they tell you that standard temperature is 273, as well as 0 degrees Celsius, which means that you cannot use 0 degrees Celsius. You have to use 273 Kelvin. So your first temperature, T1, equals 273 Kelvin pressure. Now, the deal with pressure is that you have 2 different units here, 101.3 kPa as well as 1 atmosphere. You actually can use either one of these. It depends on what the problem is giving you. If the problem says to you, the second set of conditions, the temperature is now, I don't know, 400 Kelvin, and the pressure is now, T2, and P2, the pressure is now, I don't know, 4 atmospheres. When you go to pick your initial pressure, my suggestion to you is, if they give you atmospheres, you pick the unit of atmospheres because that's what they're giving you. Pressure, standard pressure in atmospheres would be 1 atmosphere. So let's say that they tell you you're at STP and the volume was 500 milliliters. And they want you to solve for volume 2, that would be your X. We picked this particular unit because it matched. Now, let's just say in the same problem, instead of it being 1 atmosphere, you know, this problem, they were telling you it was, I'm totally making these numbers up right now, 409 kPa. Well, instead of picking 409 atmospheres, we would have to keep it consistent. So when we set up our math, we would actually pick 101.3 kPa to do this math instead. So I am going to take a minute really quick and just take a look at what is going on the remind, see if we're blowing up. We got a message. Okay, and Lisa says, do you have to use Kelvin in calculating heat? Okay, so are you talking about heat, Annalisa, in terms of like Q equals MCAT and Q equals MHV? Then no, you can use Kelvin and Celsius interchangeably. That's not a problem there. You can only use Kelvin when you are talking about the combined gas law, P1, V1, T1. That's when you can only use Kelvin and not Celsius. You can use Celsius in the Qs and Ms and all that stuff. So I'm just going to take a quick peek also at the stream that's going on the side. Yes, it says use the green. I will use green more often. My 2-year-old was in charge of my reference table. It was a bad idea. Too much wheels over percent abundance. Yes, I can do percent abundance. Parts per million is not the same as abundance. 760 millimeters of mercury in torr. You are absolutely right. You could use those, but you're not going to see them in the day of the Regents exam. The Regents uses milliliters. Sure, it could use liters or milliliters as long as the units are kept consistent. Geo, yes, I do sang only when my daughter's being really bad. And I think I hit everything right now on the live feed? I think I did. Okay. So that is everything combined gas law that we need to go over in terms of the equation. What you do need to know about this is that you are comparing the same gas at two separate conditions. So if you were to take this gas in this set of conditions right here, and you were then to turn around and change the conditions, let's say you are exerting more pressure, then these gas particles would be squeezed in more. I'm not changing the number of particles from the condition number 1 to condition number 2. One of the questions that shows up regularly on the Regents exam is compare the number of particles in the gas at first condition versus second condition. And the answer is that the number of particles is always going to stay the same because you cannot create particles. You cannot destroy particles. You can only have the same number of particles. It's kind of like the law of conservation in math. Conservation of energy, conservation of charge, and conservation of mass. So the number of particles will always stay the same. All you are doing is changing the conditions, which means you're changing the temperature. They can spread out more. You're changing the pressure, so you're crunching them in. You're changing the volume, but you're not changing the actual number of particles themselves. The number of particles are 5 here, the number are 5 here. It's just that you have changed the conditions, so they take up less space, or they move more, so they have more space. The number of particles will always stay the same. Now, there was another thing that came in on the Google form. The number of particles that, hold on a second. I'm just reading the live feed. Can you eat the particles? I never tried that. I never tried eating them. Okay. The other thing that showed up on the Google form was a question about Avogadro and his law, and doing math with it. You will never need to do any sort of math with Avogadro's law, but what you do need to know is that if you have two gases, and those two gases have the same exact conditions, meaning they are at the same temperature, which means they have the same amount of movement. If they have the same pressure, which means that they have the same amount of force exerted on them, so they are confined to the same amount of space that they can take up, and you have the same volume, you are going to have the same number of particles. So there's questions that show up on the Regents exam where it's like, you have gas A, B, C, and D. A is at 1 liter and 273 Kelvin, and it is at 1 atmosphere. And they're like, which one of these has the same number of particles? And B is like 2 liters, and it's the same. And C is like 1 liter, but it's like 400 Kelvin and 1 atmosphere. And then you got answer choice D, which is like 1 liter, 273, 1 atmosphere. Well, these two have to have the same number of particles, even if this is like H2, even though it's diatomic, and this is like, I don't know, sodium gas, they will still have the same exact number of particles in the container because they have the same conditions, which means that they have the same exact number of particles. And when I mean by particles, not like number of atoms, I am talking about particles. This would be a diatomic element particle, and this would be like a monatomic atom for sodium, which means that these would still have the same exact number of particles. Okay, I am looking at the scroll. Okay, and let's move on. That is everyday gas laws that I can think of. I'm going to give you like the next 30 seconds, not even like 15 seconds, if there's anything you want to I know, yeah, my dogs are outside and they're barking, they're crazy. The delivery guy just came with the pizza, and I know it's not it's like 9:30. You don't necessarily need the same pressure. In terms of the Regents exam theme, I will tell you that the way the Regents exam asks it, it has to have the same exact conditions. So when you're talking about, you know, having the same number of particles, that's what the Regents exam usually looks for. Now, somebody just said, Seema said, she said empirical and structural formulas are not on it. Yes, they are. they are on it, but they are not on it in the sense that you have to calculate them from the percent composition, which would be like you'd have to do molar ratios, you know, go from grams and moles and determine the number of moles and figure everything out. The number of particles, number of molecules are the same thing or no? Yes. Don't be fooled. When you talk about molecules, a molecule is something that is bonded covalently. So this could be a diatomic molecule. Okay, this would be like an atom. Okay, but this would be a particle, because this is what you would find, like with something like H2, you would find them as a diatomic molecule, but this is an atom. So don't necessarily say that all particles have to be molecules, because this is an atom, this is not a molecule. Okay? All right, so I'm just going to take a minute right now to just give you, like, not even like 30 seconds to just text in if there's anything that you want me to address that is gas laws related before I move on to the next topic.
No, it's actually now like 4 seconds. You know, all our space is ready.
Okay, so let's move on. The next thing that I want to address with you, so that was gas laws, we're going to move on. The next thing that we want to talk about here is matter, and I see that Newt just said something about monatomic elements. We will go there in this time. Let's talk elements, compounds, and mixtures, and separating mixtures and all that jazz. And there's like a hot debate right now about molecular mass, number of moles. Hold all of that. I can get into that as well. And I'm just checking the remind because Danny McDonald just sent something in. Isn't a molecule? So is a molecule and an atom both particles? Yes. Hold that thought. Let's go over elements, compounds, and mixtures right now. So let's do this. We're going to need a black pen for this. So matter is anything that has mass and takes up space, so anything that has mass and volume. And the idea is that you can have elements, compounds, and mixtures. When you talk about an element is made up of only one type of atom. So if I were to draw a particle diagram for you, this would be a particle diagram of an element because it is just one type of atom. Another thing that you need to keep in mind here is that we would call this pure because there's only one type of particle in this particle diagram. Now, if you were to take a look, there are these things that look like this. And this is like one of the biggest misconceptions that I see out there. This would be an element still. And it is still an element because how many different types of atoms are in this container? There is still only one type of atom. The distinction is that these two are found in pairs. They are together at all times. We call these diatomic elements because they are always found in pairs, and this would be what we call the Hofbrinkel or Brinkelhof, depending on who you talk to. It's like potato, potato, tomato, tomato. These are all found in pairs. Now, if I were to describe this in like one really easy way for you, these are like the girls at parties who always have to go to the bathroom together. God forbid they go all by themselves. They will die a horrible death because they always need to be in pairs at all times. They just cannot be separated. Well, they can be separated, but you get the idea. Okay, these are always found in pairs in nature because that's just the way they are. And again, this is still an element because it's only one type of thing, atom in that container. Now, this is still an element and we would still call this pure. Next particle diagram. So, somebody just said, Jody, can we at some point run through the different types of orbitals really quick? No, only because it's not on the Regents exam. And if you want to go over that, we can absolutely do that another time, but I don't want to waste your time with something that you're not going to see the day of the Regents exam. So, wait a second. You just said orbitals. Orbitals are regions of probability. where you find an electron, that's atomic theory. That is different from SPDF orbital notation, which is what I think Jody was talking about, where she said orbital. So with that, Jody, I am not doing orbitals with SPDF. I can mention orbitals really quick if you want when we talk about atomic theory. And yes, aqueous is always homogeneous, and yes, it is a mixture. Hold that thought. So the next particle diagram I want to draw for you is this guy. Now, this is not an element because it has two different types of atoms in this particular picture. Now, the next thing that happens here is that kids are like, oh, so it's not an element. So that means that it has to be, I don't know, a mixture because it's two different things. People always tell me that this is not pure, which is the biggest misconception going. There is only one type of particle in this container. Here, there is one type of particle, and all of the particles are the same. If I reach in and I pull out one of these particles, it will always be a white circle. Here, there is only one, so particle, particle, particle. Here, there's only one type of particle in this picture. It will always be the same particle if I reach in and pull it out, which would be white bonded to white, even though they are the same because it's still the same atom. Here, there is only one type of particle. If I reach into this diagram, the only thing I will pull out is white bonded to black, which makes this still pure. This is what we would call a compound. And a compound is two or more different atoms that have chemically combined into a chemical compound. If I would like to get white away from black, I have to pull it out and then I have to break it chemically because they are bonded together. This is a compound. It is still pure because there's only one type of particle in that container. Particle, particle, particle. Atom, molecule, molecule. Do not get into the idea here that a particle has to be a molecule, because it doesn't. It could be an atom. Somebody just sent on the live streaming thing something about which cannot be broken down chemically. Elements are pure. They are found in their elemental phase, elemental form. You cannot break down an element because this is the smallest thing that is out there that still has the identity of that element. Don't get me wrong, there's like protons, neutrons, and electrons in here, but they are not going to be, they're not going to still have that same identity as what you have in this particle diagram. Okay, now, again, I'm just looking through. Any tricks for remembering homogeneous is different and heterogeneous is the same? You actually flip those two. I will go over that in a minute. Somebody said something about acids and bases. I feel like it's like absolutely everything in chemistry. Yes, the RJG viewer 15, acids are covalent. You are right, acids are not ionic. Hold that thought. I guess we could go through that if you give me time. So let's move on here. This is pure, this is pure, this is pure. I can only take out one thing, one particle, one type of particle, one type of particle. Even though it looks like it's not, it's still one type of particle. Now, if you were to have something that looked like this, this is what we would call a mixture. And the deal with a mixture is that a mixture is going to be physically combined. I don't really like that word. Physically mixed together, which means you can physically separate the different particles. Now, if I reach into this container, I have a 50-50 shot of pulling out black, or I have a 50-50 shot of pulling out white. And the idea here is that you have two completely different particles that have been physically mixed, so this is not pure. This would be a physical mixture. Okay, somebody's asking me the difference between heterogeneous and homogeneous. Hold that thought for a minute because we can absolutely go over that. And I'm just going to take a break really quick. Is there anything that you want to ask me in terms of elements, compounds, mixtures? Who just said what? Okay, Fahim just said, why isn't it pure? The reason why this is not pure is because if I reach into this container, I can pull out black or I can pull out white. There is options here. In this picture, the only thing I can pull out is white bonded to black. There's only one type of particle. This particle is a white bonded to a black. Here, I can only pull out one particle. Here, there are two different options of particles. There's a black particle, there's a white particle. They are just physically in this container, which means I can physically separate them. Okay, so you just said mixtures can have varied composition. You're absolutely right. This particular compound is a white bonded to a black, which means like there's a white and a black and they are always together. That is the ratio they are found. This is like saying HCl. You will always find an H and a Cl together. You can't have HCl2 because then it wouldn't be the same compound. Here, this is like saying you have a mixture. Well, you can have an equal proportion of black and white. You could have more white. You can have, more black. This, it doesn't matter. A mixture can have varied proportions of the different particles, whereas this compound, it will always be found in a fixed proportion because that is how it is bonded together. Okay, somebody just said, what is chromatography again? Hold that thought because we're going to talk about separating a mixture. Okay, I'm going to take this down. I'm going to give you like 10 seconds if there's anything you want to text in via the remind, and also if there's anything that you want to leave on the streaming feed. Okay, someone just said, is air a heterogeneous or homogeneous compound? Just take a look really quickly. Fel 0246, look around you. Can you see the different components of air? Can you see carbon dioxide, oxygen, nitrogen, all those different things? Just look at it. If you can see the different parts, it is heterogeneous. If you cannot see the parts to the naked eye, it is homogeneous. So look around. Can you see the different parts of air? I can't tell them apart. Air is homogeneous. So let's move on here. So one of the things that Fahim just said, what is the opposite of a pure substance? A mixture. A mixture is the opposite of a pure substance. Fahim, you just said air is heterogeneous. Air is not heterogeneous because you cannot see the different components. So let's take a minute really quick and let's draw what I like to call the flow chart of matter. Matter can either be pure or matter can be a mixture. Okay, if matter is pure, you have two options. It can either be an element or it can be a compound. Now, elements come in two forms. You can have the monatomic elements, which would look like what you drew, monatomic, which would look like what we drew first. They are all single circles by themselves, whereas you can have diatomic elements. This is really messy. Matter is either pure or matter is a mixture. Okay. If you have an element, you can have monatomic elements, and monatomic elements would be one circle by themselves, whereas you can have diatomic elements, which would be like your Hofbrinkel or Brinkel-Hof, depending on who you talk to, where they are found together in pairs. Compounds are going to be two different atoms, two or more different atoms bonded together, but they are still considered pure because they have two different atoms or more chemically bonded together. Now, in a mixture, mixtures can either be homogeneous or mixtures can be homogeneous, or they can be heterogeneous. And somebody asked, heterogeneous. Somebody asked, well, how can we remember them, tell them apart or help you remember? Okay, homo means the same, whereas hetero means different. Okay, and not to be like all weird and creepy or anything, but if you are a heterosexual, you like the opposite or different sex, whereas if you're homosexual, you like the same sex, which just helps you remember the difference between homo versus heterogeneous. That's the difference right there. So now this is actually really tricky because sometimes kids are like, oh, homogeneous means the same, so everything has to be the same. Well, if it's the same, then it would be pure. Notice that homogeneous is not on this side with the pure things. Homogeneous is like a misnomer, kind of. Homogeneous means that it appears to have the same makeup to the naked eye. As opposed to heterogeneous means you can clearly see the different parts to the naked eye. Okay, so somebody wanted blue, so let me draw a little blue for you, because apparently you don't like orange. So I'm going to come back to this flow chart in a second. Let's draw a little picture for you. So I'm about to tell you a real life story. When I was in college, I had a series of unfortunate breakups, and my college roommate came home with my new boyfriend, and his name was Mr. Wright, and he was a fish that lived in an Erlenmeyer flask. So Mr. Wright and his Erlenmeyer flask fish tank is the classic example of a heterogeneous mixture, because you can clearly see the different parts. There's a rock. Last time I checked, it was solid. Mr. Wright was a fish. Last time I checked, he was also a solid. And the stuff that Mr. Wright is swimming in, well, this is a little bit tricky. It could be pure water. And if I were to draw a particle diagram for you, it would be like little water particles. Or it could be salt water, because he could have been a saltwater fish. And if it was salt water, well, it will be NaCl in the aqueous form, which would mean AQ. Somebody just said that the only thing you need to know about homogeneous mixtures is that they are solutions. That's not necessarily true. No, I did not date a fish. Not really. You need to know about homogeneous mixtures that they are solutions. That's not necessarily true. You do need to know how to separate a homogeneous mixture, so hold that thought for a second. Now, with a heterogeneous mixture, you need to know that you can clearly see the different parts, and if you would like to separate a heterogeneous mixture, well, then you can use this method called filtration. And the way filtration works is you are going to take a funnel, okay, and you are going to pour the contents of Mr. Wright's fish tank into the funnel, and you are going to separate these different components based on their phases of matter. You need to have a solid in order to do this. Now, my college roommate came home with Mr. Wright, and I was like, yes, I finally have a boyfriend who's awesome. And just like every other situation that was going on, he pretty much like kicked the bucket like 2 days later. So when he kicks the bucket 2 days later, I'm like, what am I going to do with a dead fish? So we took Mr. Wright and we dumped him down the toilet. Now, I really should have taken a funnel, and we should have funneled Mr. Wright through a funnel, you know, with a piece of filter paper. Because what happened was that I dumped Mr. Wright and all of the contents into his fish tank into the toilet bowl, and the water went down, the salt water went down, no problem. Mr. Wright, no problem, went right down the toilet. And then there was the rocks. Well, rocks are really, really dense, and when you dump them into a toilet bowl and you flush the toilet, rocks don't flush down the toilet. So when all my friends came over earlier that week, they were like, why is there rocks in your toilet? What's going on? What's happening? So we kind of needed to filter this situation so that the rocks would stay in the filter paper because they don't pass through the filter. Mr. Wright would stay into the filter paper, and this would be like the toilet bowl. I'm not going to really draw it for you, but basically all of this stuff would pass through, and then we could then flush all of this liquid / aqueous stuff. So this is how we would separate a heterogeneous mixture. You can separate a heterogeneous mixture by using filtration because you have solids and liquids or solid and aqueous in the same exact container. Yes, this would be an aqueous solution. Hold on a second. Somebody just said, is aqueous homogeneous? Yes, aqueous is homogeneous, but that is not the only thing that's in this picture. In this picture, you have a fish and a solid. So this entire thing right here would be a heterogeneous mixture. If you are talking about salt water itself, salt water is an aqueous solution, which basically, if you were to filter this, well, then the fish would stay on the filter paper, the rock would stay on the filter paper. The aqueous solution, which would be the NaCl, and the water would pass through the filter and then end up in the toilet bowl. So let's just take a quick second really quick because I am now going to turn around and talk about homogeneous, and I just want to hit the pause button so the delay can catch up, and if there's anything that you want to ask me about this picture and heterogeneous mixtures and how to separate them, I'm going to give you 10 seconds to text in. Okay, Fahim just said, I thought it can't be pure water and salt water. You are right. Pure water is not salt water. I guess my point here is that in my fish tank, if I were just to look at it, I wouldn't know if this was pure water or salt water because to the naked eye, you cannot tell them apart, which is actually where we need to go right now. This right here could be a homogeneous mixture to the naked eye because you can't tell water, pure water or salt water, apart from the naked eye. That is why it's a homogeneous mixture, because to the naked eye, it appears to be one substance. Now, the deal here is, after Mr. Wright, well, what did I just do? Hold on. Okay, more comments. Okay, so after Mr. Wright kicked the bucket, here is the funnel. And here's a piece of filter paper with the rocks and Mr. Wright, who's now dead. And we just poured all of the contents of his Erlenmeyer flask into this funnel. And here is the container with the liquid that just passed through. And humor me for a minute, this liquid is going to be saltwater aqueous. Now, okay, see, I can't say your name, Ashish. The hell? Just said, so aqueous can be homogeneous or heterogeneous. No, aqueous is always homogeneous. I'm going to put this picture back up right now. In this picture right here, this entire Erlenmeyer flask situation is a heterogeneous mixture because I can see the fish and I can see the rocks and they're solid, and whatever substance this fish is swimming in is going to be something that looks like, you know, pure water or salt water. I guess my point here is that it is indistinguishable to the naked eye because pure water looks the same as salt water because salt water is a homogeneous mixture. Now, this fluid he's swimming in could be pure water or an aqueous mixture, but the whole entire thing is going to be a homogeneous mixture. And yes, pure water is a compound. So let's talk about this situation right here. Once we filtered Mr. Wright out and the rocks, you now have this aqueous NaCl solution. Now, in this aqueous NaCl solution, if you were to get like all up close and personal and take a peek at what's going on, you would see that there's little tiny water molecules that are swimming around, and they're like, we're water molecules. And at the same time, you are going to have NaCl, which is dissociated into its ions, floating around. Now, to the naked eye, this appears to be one substance, but in reality, it is not one substance. It appears to be because the particles have fully dissolved into each other. The particles have a uniform distribution or an even distribution, which makes it impossible for you to the naked eye to tell them apart. Now, in this picture, even though to the naked eye we can't tell them apart, if you were to get like all up close and personal, you would see that there's water molecules and you would see that there's also NaCl hanging out in this beaker. Now, we already passed this through the filter, so we know that we cannot use filtration because the particles have been fully dissolved. Fahim just said NaCl is homogeneous because it dissociates. NaCl aqueous is homogeneous because the particles fully dissolve. You can put sugar into water and it would still be homogeneous because the particles fully dissolve, but NaCl will dissociate, whereas sugar will not because NaCl is ionic, whereas sugar is covalent. It has nothing to do with the dissociation. It has to do with the fact that it is fully dissolving into the compound. Into the water. Fahim also just said, how do you know if a reaction dissociates? Hold the thought really quick because I can go through that in a minute. All right, so let's talk about this picture. And basically what's happening here is you have these particles and they are fully dissolved or uniformly mixed. You cannot use filtration because they are uniformly mixed. Now what happens here is that you can separate this, but you have to use a different method. And the name of this method is called distillation. Have you ever heard of distilled water? With distillation, you are going to separate these things by their boiling points. Separate by boiling point. Now, water will boil at 100 degrees Celsius. NaCl is going to boil at something like 500 degrees Celsius, which do not quote me on this because I'm not entirely sure about that exactly, but it's going to be a higher boiling point. Now, what happens here is that when you start to boil this salt water, you are going to reach 100 degrees Celsius first. So these little water molecules are like, we're dissolved. And all of a sudden you hit 100 degrees and the water molecules are like, peace out. And they leave in the form of a gas. Now, in this container, once all the water molecules are gone, the NaCl is like, yeah, we don't boil until 500 degrees Celsius, and they're going to stay in their solid form on the bottom. What you need to know with distillation is you can separate them by boiling point. Because you have physically mixed them, you can physically separate them. Because you have physically mixed, you can physically separate them by their boiling points. Okay. Okay, Sarah J just asked, what is the difference between dissociation and dissolving? Hold that thought for a second. I can do that for you in a minute. Okay. Okay. So let's just go back to this for a minute. If a mixture is homogeneous, it appears to have the same makeup to the naked eye, but the particles are evenly distributed. If you would like to separate a homogeneous mixture, you are going to use distillation, which separates them by boiling point. If you are going to do a heterogeneous mixture, you can use filtration because you are going to have different phases. And if you want to use filtration, you have to have a solid in there so that it stays in the filter paper. Now, there is actually one other method of separating a mixture, which is called chromatography. And the deal with chromatography is you are separating different components based on solubility and based on density. Someone just said 8 minutes left. Don't worry, I will keep going for a little bit longer until I quit. Okay, with chromatography. Okay, you actually saw chromatography when you took the living environment. And do you remember learning in the living environment there was a state lab, which by the way, I also teach living environment. there's a state lab where you were tasked with determining which plant was most closely related to the magical plant called Botanicurus, which magically cured cancer, which, by the way, it was all a hoax. It was all fake. And basically what happened was that you had a green pigment. And basically that green pigment, they were like, this extract came from the magical plant called Botanicurus. And then you have like plant X, Y, and Z. And the deal here is that you wanted to see which one was most closely related. So what you did was you took water, and it was like in a big container, and you had a sample of X, a sample of Y, and a sample of Z. And not for nothing, okay, these are all green pigments, and to the naked eye, it looks like it's the same exact thing because it's different components of a mixture. Now what happens is that all of the water is going to start to travel up the paper. And the way this works, if you even think about earth science, which by the way, I teach that sometimes too, when you think about earth science, you remember learning things about like deposition of like rocks and like sedimentation, and how like in like water beds of like rock erosion, how like heavier rocks will be deposited first, whereas the smaller rocks will travel further, right? So the same thing in chemistry, if you would like to separate things using chromatography, the way this works is that you have like blue pigments, right? And Botanicurus had a blue, and let's say Y had a blue, and Z had a blue. Z would be like the lighter pigment, and then there would be like an orange pigment, and let's say there was, I really should have another color, another green pigment. And basically what this is going to do is it's going to separate these different components based on their densities. And you in the living environment are like, well, which plant was like the magical plant that cures cancer? And you're like, oh, look, Y is the only one that has all the binds, you know, bands. So clearly this guy is most closely related. So the idea here is that you can use chromatography to also separate a mixture. This is a mixture, and that's a mixture, and these are all green mixtures, but these green mixtures had different components in them, and you can use chromatography to separate the different components based on density. Okay. Okay, so I'm going to give you guys a minute while I just check off my list of things that we need to do. So somebody said elements, compounds, mixtures, we're done. Separating mixtures, we can touch allotropes for like a hot second. We can dive into bonding, and when I hit bonding, I can talk about intermolecular forces of physical attraction, where I can also discuss dissociation, because someone said what's the difference between dissociating and dissolving. I can go there in a minute. That's when that's going to happen. I'm also just going to check really quick the side feed of what's going on. Someone said, can we go over polarities too? Yes, I will do that when I hit intermolecular forces of physical attraction. She said, if I mix grains of salt and grains of sand, it is not aqueous because I can clearly not see the difference. The definition of aqueous is that it has to be mixed with water and fully dissolved. So if you mix salt and sand and water, then it's not going to be aqueous because the sand is not going to fully dissolve. But if you are going to mix salt and water, that would be considered aqueous because it is mixed with water and it is fully dissolved. Okay, and somebody just said, you're right about ionic bonds and higher boiling points. I will go over bond properties when I get here and I talk about bonding, and that was dissociation. Okay, fantastic. Just checking the bottom again really quick. Okay. Okay. Someone said, please go over catalyst geo. I can do that. I'm not there yet, but I will. I promise. Okay. I will do catalyst after I do bonding, sig figs. Somewhere in here I'll touch catalyst. All right, let's talk bonding really quick. Okay. Okay, so things bond because they are trying to, oh, wait, we're not ready for this. Somebody just said allotropes, because an allotropes go in matter and energy. Allotropes. Okay. Allotropes are something like carbon in diamond and carbon in graphite. Both of these are made of carbon. So if you were to look at like a particle diagram, you'd be like, oh, look, they're all carbon, carbon atoms, carbon atoms. However, the carbon in diamond versus the carbon in graphite, they are bonded or attracted to each other in a different crystalline structure. In graphite, and again, I am like totally improvising, like I don't know this exactly for sure, but I know the bonding pattern of graphite is more sheet-like structure. So it's more like 4 bonds at a time, and like, you know, this linear, and like it sheets on itself, so it looks like this, as opposed to carbon and diamond. And in carbon and diamond, the carbons are more compacted, and I know carbon can't make this many bonds, but you get the idea. But it's more of like a compacted structure where the different the atoms are arranged in a different structure, which then give them different physical properties. Okay, diamond is not the same as graphite. Graphite is what you find in a pencil, like a mechanical pencil, whereas you know, a diamond is like in a diamond ring. Now, if you were to look at the atoms of diamond and the atoms of graphite, they're going to have the same exact carbon atoms, but because they have a different structural arrangement, so different structures, it gives them different properties. So the deal with allotropes is different structures and different properties. Now, this is like, I would say to you, like 90% of the time, if they ask you about allotropes, these are the big ones: carbon and diamond and carbon and graphite. That is not the only allotropes that I've seen them use before. I've also seen them use the allotropes of molecular oxygen and molecular ozone. These are both made of oxygen atoms. Now, oxygen atoms, like, oxygen O2 is like the stuff that's like safe to breathe, whereas like ozone is like what you find like in the atmosphere, and also like what you find in like photocopy machines, which is like carcinogenic. Again, like different structures, even though they're made of the same atoms, they have different structures which give them different properties. I would say to you this is like 8% of the time, so like carbon in diamond and carbon in graphite is like 90% of the time. Okay, that's like 2% left. Your remaining 2% is like absolute crapshoot. One time I saw them do red phosphorus and white phosphorus. They're both phosphorus, but they have different properties, which implies that they have different structures. And like the possibilities are actually endless, but like these are the two, and I'm going to do this all over again if you watch my live stream from before. These are the two the Regents loves, and they are found like in really big quantities. So these are the allotropes that the Regents exam likes to look at. Somebody just said, are allotropes isomers? No, isomers are different. Isomers are compounds, whereas allotropes are still in atoms. Like this is still, if you were to draw this out, like, and you were to look at like carbon and diamond, well, carbon and diamond would all still be carbon atoms, whereas like carbon and graphite would like still all be, but they would be less, you know, more spaced out. These would still be oxygen atoms. Phosphorus and phosphorus, white and red, still atoms, as opposed to isomers, which is a different structure with the same number and types of atoms, but it's a compound as opposed to elements. So that is the deal with allotropes. Okay. Bonding. The reason why things bond is to achieve stability. And the definition of stability in chemistry is a full valence. And the definition of a full valence, 99% of the time, is that you have 8 in the valence for like pretty much everybody except hydrogen and helium, which are totally fine with 2 in their valence. And the reason why this is a story for another day. It has to do with sp D, F configuration, which we are not touching with a 10-foot pole. But the idea here is that things bond in order to achieve stability. 8 in the valence is the magic number, except if you're hydrogen or helium, and then there's only 2. Now, there are 2 different ways to achieve stability in chemistry, and it comes down to what's already in your valence. Let's say for a minute you had somebody like sodium who has 1 in his valence. 1, and okay, 1 in his valence. Now, sodium is hanging out with his pal, his lady friend, chlorine. Sodium has 1 in his valence, and his lady friend chlorine has 7 in her valence. Now, if you were to take a look at sodium's electron configuration, his configuration is 2, 8, 1. So if you were like draw like a Bohr diagram, he would have like 11 protons, maybe 11 neutrons. I'd have to look at the mass, and this would like be his Bohr diagram. So sodium has 1 in his valence. As opposed to chlorine, who has 17 protons in his nucleus, maybe 18 or 17 neutrons. Again, I'd have to look. And his configuration would read 2, 8, 7. Now, in this particular situation here, you have sodium who has 1 in his valence, and sodium's like, I need to achieve stability. I have 1 in my valence. Would I rather lose 1 in my valence? Because if I lose this 1, I have 8 hanging out underneath. Or would I rather try to gain 7 in order to complete my valence? At the same time, chlorine's like, I already have 7 in my valence. Chlorine says, would I rather try to lose all 7? Or do I want to try to just gain 1 from somebody else? Sodium turns around and goes, well, I have 1 in my valence. It's actually really easy just to lose 1 electron. And he's all like, all I ever wanted to do in life was lose my electron. At the same time, chlorine's like, all I ever wanted to do in life was gain 1 electron. This is a match made in chemistry heaven, because the sodium is going to lose his electron to the chlorine. The sodium does not want this electron anymore. The chlorine is like, I always wanted this electron, and he just takes it, and that's the end of the story. This is a match made in chemistry heaven. This is called an ionic transfer. The reason why it is ionic, because this sodium is now an ion. This sodium had 11 protons in his nucleus, and protons are positive. He had 11 electrons in his shells, which means overall this entire thing to start with had a charge of 0, which made this sodium atom. After this has happened, the sodium still has 11 positive protons in his nucleus, and now he only has 10 negative electrons. If you combined positive 11 and 10 negatives, you end up with positive 1. Now, I get kids all the time who are like, but I lost an electron. Isn't an electron like losing? Like if I lose it, shouldn't it be negative because I'm losing it? That would be true if this was like normal common sense, but when you lose an electron is negative. And in math, if you subtract a negative, you end up with a positive. And if you can't wrap your mind around it, just look at the math here. You had 11 protons, which are positive, and 11 negatives, which was 0. When you lose this 1 electron, the balance is off. 11 positives combined with the 10 negatives that were here gives you a charge of +1. So this sodium just became +1. On this side, over here, chlorine started off with 17 positive protons in his nucleus, her nucleus. In the beginning, she had 17 electrons total in her shells, which means she was an atom because her charge overall was 0. Once this ionic transfer has happened, you still have 17 positive protons in the nucleus, but now you have 18 negatives. And if you combine 17 positives and 18 negatives, you end up with -1. Now, again, kids are always like, but I gained. Shouldn't it be positive if I gain something? Here, if you are gaining, you're actually gaining a negative thing, which means that this becomes positive, negative. And if you don't believe me, do the math. So It's not a minus, it's a plus. So in this diagram right now, we would call this an ionic transfer, which means that this would be sodium plus 1, and he would get a bracket because we have changed his valence. And this chlorine would be -1 because we changed that valence, and this would be an ionic transfer. Now, somebody just threw out there, can you do the half reactions because it helps? Sure, let's do that. What happened here is that this sodium started off as sodium atom, and at the end, it became sodium plus 1. By the way, this is a redox connection, so if somebody said do the half reactions, here we go. If you were to take a look at this, this numerical value is becoming more positive. Now, in chemistry, when you lose electrons, losing is positive. So if you assess these oxidation numbers, you're going from 0 to +1, which means you are becoming more positive. Yes. Okay. Which means you're becoming more positive. We're going to put the electrons in a minute. This chlorine started out as chlorine atom, and at the end, it became chlorine -1. In chemistry, gaining is negative. So if I assess this oxidation value, it's going from 0 to -1. Somebody just said, do you have to put the brackets? Do you have to draw the brackets around the metal? Technically no, but I always put brackets around anything because I think it's easier just to bracket everything. And you're not wrong if you bracket everything. And it really doesn't matter. The charge should be on the outside, but that was just me because it's 10 at night and I'm an old lady and I'm tired. So let's go back to this sodium. This sodium is becoming sodium 0 to sodium +1. Losing is positive in chemistry. Now, somebody said write out the half reaction, so here I go with my redox. Not only is losing is positive, losing is also has a fancy chemistry name called oxidation. And I use the acronym LEO. Losing electrons is oxidation. In chemistry, when you gain, gaining has a fancy chemistry name called reduction. It's the same exact thing, just using its fancy chemistry name. And I use the acronym GER. Now, some of you like to use oil rig. It's the same exact idea. But the reason why I like to use LEO and GER is because it also helps me remember what's happening in terms of the charges. So here's Leo. Leo is normally a super happy, positive lion. He's like, I'm a lion and I'm so happy and my name's Leo. Now, when Leo gets really angry or negative or just pissed off in general, and he's negative, well, angry, negative lions go, grr. So when the lion is angry, he's like, I'm so angry. That is when he says grr, because gaining electrons is reduction, and we are looking at a more negative value in oxidation number. When you do oxidation, losing electrons is oxidation, and Leo is normally a happy, positive lion. This sodium 0 to becoming sodium +1 is going to be more positive, and more positive is Leo because he's like a happy, positive lion. Over here, this half reaction would be negative, like more negative, because the lion's going, grr, I'm so negative and angry, and that helps me remember. Now, when I lose electrons oxidation, the other thing that I always like to do when I do redox, and I feel like I'm like jumping around from like all these different topics because somebody said do the half reactions while you're at it. So let's throw that in. When I do half reactions, I like to write them out when I balance them with both electrons on either side. Like I put placements here because this is almost like my self-check. Now what happens here is that I like to cut the reaction in half, and I like to call this side the enter side, which means like the reactants. Things that enter are called reactants, whereas things that exit are called products. Hold on one second, I just hear my phone blowing up. Okay. Danny McDonald, yes, NaCl has a boiling point. It's super high. Like I said, 500, but I'm pretty sure it's like on the order of a couple thousand. Danny McDonald said, does redox come from reduction and oxidation? Yes. The deal with redox is that the read is reduction, which means that somebody has to gain, whereas oxidation is the fact that somebody is losing. Redox is a two-player game. In order for somebody to gain, somebody had to lose. So basically what happens here is it's called redox because somebody has to lose. One of these is going to be called the reduction half reaction because that's only half of the picture. In order for somebody to gain, well, somebody had to have lost, which is the other half, also known as the oxidation half reaction. So back to this, when I do my half reactions, I like to put spots on either side because it shows me like where all the electrons could possibly go, and it's almost like a self-check. On this side, these are the things that are entering, which I call the reactants because they're entering the reaction, whereas when they exit, it is going to be your products. So when you lose something, it is exiting your possession. Like, I lost my car keys. They're out of my possession. I don't know where they are. Whereas when you gain something, it enters your possession. So let's take a peek at what we have going on here. This is sodium 0 becoming sodium +1. Well, more positive, I think of Leo, who's like a really freaking happy lion, which means that I am losing. And if I lose, it is exiting my possession, which means I am going to put the electrons on this side. And this is a 1 number change on the number scale, which means that I lost 1 electron. Down here on the bottom, this is going from 0 to +1, which means it's more negative. And when I think of negative, I go, because Leo's really angry. And when he gains electrons, that's reduction. When I gain, it is entering my possession. So I'm going to put the electrons over here, and this is a 1 number change on the number line, which means I entered 1 electron. Now, this is your self-check because Danny McDonald just said, why is it redox? Well, someone has to gain. Well, the chlorine gained electrons, but somebody had to lose, which means the sodium had to lose over here. If I had both of my electrons over here, well, that means that we have 2 losers, and that's just never cool because that doesn't work. If we had 2 gainers, well, again, that doesn't work because somebody has to lose and somebody has to gain. So when I finally balance this out, I just do a little shade, get rid of it because it doesn't belong there, but at the same time, it is showing me that somebody is losing and somebody is gaining. Now, this is actually balanced in terms of redox because the number of electrons that are being lost is equal to the number of electrons that are being gained. Okay, just taking a pause and watching the live stream because it's just a few seconds behind. Okay, so that is the deal here with ionic bonds and ionic transfers. We're going to come back to covalent in a minute because I feel like I should hit formula writing at the same time while we're doing this. Now, when I write the formula for sodium chloride, sodium is a +1 charge and chlorine is a -1 charge. Now, what we do in chemistry is we do this thing called the crisscross, which tells us the number of atoms we need to satisfy this particular, the number of each type of atom we need to satisfy the compound. So this would mean that I would need 1 chlorine and 1 sodium, and I do not carry the charges down for me, the signs down with me. The top value is the charge, and the bottom value is the quantity of the atoms. Now, what happens here is that this happens to be a match made in chemistry heaven because the number of electrons that sodium lost was equal to the number of electrons that chlorine had gained. let's do something a little bit more real life. Here's barium. Barium's like, I have 2 in my valence, and chlorine is like, I have 7. Barium is like, all I ever wanted to do in life was lose 2 electrons. And chlorine's like, all I ever wanted to do in life was gain 1 electron. So they go home and they do this little thing called swapping valences. And this barium is going to satisfy chlorine's valence. So the barium is satisfying chlorine's valence, and chlorine's like, now I'm so satisfied. This chlorine is like, this was awesome. This is awesome. I'm so satisfied. Barium is like, what the heck? Not satisfied. Not satisfied at all because I really needed to lose 2 electrons. So in order to make this happen, barium is like, I'm so great it was good for you, chlorine, but really wasn't that great for me. My valence is still not satisfied. In order to make this a happy situation, we actually need a second chlorine or somebody else to fully satisfy barium's valence. So the barium sends his electron over to this second chlorine. The chlorine gains that electron. This barium now has a +2 charge, and this is now satisfied. Now, someone just said the RJG viewer, see element sharing is caring. Here's the deal. This is not a share. Not a share. This is a full-on transfer. Barium said, I don't want these, please take them. And chlorine was like, no problem, I will take them. There is no sort of sharing of custody of the electrons. Once the electrons have gone to chlorine, chlorine's like, thank you, out of here. As opposed to barium, who's like, I don't want them, I'm out of here. Now, in order to make this a happy situation, the barium has lost his 2 electrons, and the chlorines have each gained their electrons. So when I draw this, I want to draw this, and you can feel free to put the brackets in the middle like I do, because I think brackets for everything. Basically, the way that we would draw this is we would put barium in the middle, because barium has a +2 charge, and it is going to be attracted to the 2 negatives on either side. Okay, you really, depends on who your teacher is. I would not accept this in my classroom the day of an exam, because to me, this makes no sense in terms of charge attractions. You would never find the 2 chlorines next to each other because these 2 things are negative and they would actually repel. So we want to alternate them. You're absolutely right, whoever said that, that you would alternate these because of the charge attractions, the electrostatic attraction. So when we crisscross, you can, if you wanted to determine the number of bariums you would need and the number of chlorines you would need to fully satisfy everyone's valences, you could draw all this out. We're not going to bring you over this. You could draw all this out. Or you could do the crisscross method, which you would bring down these charges, and you would end up with 1 barium and 2 chlorines. Now, you don't need to write the 1 in because it's implied if there's only 1 that you don't need to put the subscript in. And what this would mean is that you need 2 chlorines to satisfy the valence of 1 barium. Now, when you crisscross, what you are doing inadvertently without realizing it is you are balancing the charges by balancing the mass, and you are conserving both mass and charge by doing this. Because if you were to take a look at this, you have 1 barium, and 1 barium is losing 2 electrons. And if you talk about this in terms of charge, well, 1 distributed over this, this +2 distributed over this 1 would be like +2. This chlorine, 1 of them is losing 1 electron, but you have 2 of them, which means that you are, I didn't mean to say lose, gaining. Overall, you're gaining 2 electrons, and -1 distributed over the 2 would give you -2. So if you combine +2 and -2, this overall gives you a charge of 0, which means you are balancing the charges by crisscrossing the mass, and you're getting the number of electrons to be equal to each other, which is basically what is happening if you write this out half reaction style, which we'll do, and then we'll move on because I feel like I did everything half reaction that I think they could ask you in terms of writing them. If you were to write out what is happening in this barium-chlorine story, the barium started off as barium atom, and it is becoming barium ion with a +2 charge. The chlorine is starting out as chlorine 0, and it is becoming chlorine -1. I am putting my electrons in, my spaces for them, and I am assessing them for enter and exit. So this is 0 to +2. This is becoming more positive. I think positive. I think happy Leo the lion. He's so freaking happy. And losing is an exit. So I am going to put my electrons here. This is 2 changes on the number line, so this would be 2 electrons. This is 0 - 1, which really this should be diatomic, but we're not going there. You get the idea. This is 0 - 1, so this is becoming more negative. So this means that I am gaining electrons, and I think of GR, like negative GR, and that would mean that this is 1 change on the number line, which means I am going to be gaining 1 electron. Now this works, but the number of electrons being lost is not equal to the number of electrons being gained. I can multiply this by a coefficient, which means that I would get 2 electrons, which works because 2 distributed over the 1 gives me 2. But that would mean I need 2 chlorines to satisfy this 1 barium. Now this is just another way of looking at this. We needed 2 chlorines to satisfy 1 barium. It's another way of representing this. We would need 2 chlorines to satisfy 1 barium. So that is everything half reaction / ionic that I can think of at the same time. I'm going to give you like a minute, not even like 30 seconds, just to catch up on the live feed. And then I want to just go over bonds with you, and I might be calling it a night. After that, I don't know. We'll see how much longer I can go. Okay. Okay. Sorry, I'm just looking at the live stream, and I think I heard my phone blowing up. No, I didn't. Okay. All right. So with that being said, we just dove into everything ionic. It is called ionic because there is a transfer. There is a transfer because somebody is going to lose and somebody is going to gain. Losers are your metals. Metals always like to lose because they have a low valence, whereas gainers are your nonmetals. These are your triggers right here for ionic. Ionics are always transfers. They are always losing and gaining. You always have a metal and a nonmetal, or some sort of polyatomic ion in there that you would substitute out for your positive and your negative. Now, the next thing you need to be aware of here is that when you draw an ionic compound, you need to put your brackets in, because a bracket means you change the valence, and you need to put a charge in to tell you how the valence has changed. Okay. As opposed to something covalent. Covalent is a completely different beast. Covalent would be somebody like carbon, who has 4 in the valence. Now, if your teacher taught you SPDF, they might tell you to always start with 2 on the top and work your way around, which is the way it should be done. This is like an exception to this rule. Carbon is the one time you are allowed to rearrange the valence. There's a couple other times, but this is one of them. And the idea here is that why would you share a bedroom with somebody if there's an open room down the hall? So you have my permission to rearrange carbon's valence to end up looking like this, which gives it 4 places for you to form 4 bonds. Now, carbon has 4 in his valence. And carbon goes home to play the swap valence game, and he's like, I have 4 in my valence. Would I rather lose 4 or would I rather gain 4? And he kind of just is like, well, I don't really know if one of those is more desirable than the other. He's kind of like, I don't really know what to do. And he's not clearly a loser or a gainer. He's kind of like stuck in the middle. Now, you have somebody like hydrogen who has 1 in his valence. And hydrogen only needs 2 to satisfy his valence, so he's kind of in the same boat. And what will happen is, if you were to have a carbon and 4 hydrogens hanging out, okay, you would end up with carbons, 4 electrons, and the hydrogen comes in and says, well, I want to lose 1 or I want to gain 1 to satisfy my valence, and he's really looking to gain. The problem is that this carbon is not really in the situation where he really could lose because he's got 4 in his valence. So the hydrogen comes in and he's like, I want the electron, and carbon's like, no, I want the electron. And they kind of go back and forth for like, I don't know how long. And finally they're like, let's just share. Like, sharing's caring, and let's just share them in order to satisfy all of our valences mutually simultaneously at the same time. Now, this carbon has 1, 2, 3, 4 electrons of his own, but he's sharing 1, sharing 2, sharing 3, sharing 4 with those hydrogens that are present. At the same time, this hydrogen has his own electron, but he is sharing the electron with this carbon, which means that his valence is satisfied because he has 2. This is a completely different story. This is what we would call a covalent share. When I think of I think of like cooperate, co-captain, commiserate. Co meaning share. These guys are literally sharing a valence in order to satisfy each other. This is very, very different than what you've had in this picture, where barium is like, I don't want the electrons. Please take them from me. I don't want them. And chlorine's like, yes, all I ever wanted was these electrons. Now I'm going to hold on to them for dear life because they are now in my custody. We are giving electrons away here. In this situation, there's not a clear winner. They are sharing joint custody of the electrons at any given time. Covalent compounds share their electrons. They share because these are both nonmetals and they both kind of want to gain, and they play electron tug of war and they figure it out and they're like, let's just share. When we draw, we are going to draw these Lewis dot diagrams with dots to represent the bonds, or lines. A line means to share, so I actually could substitute each of these pairs out and I would put in lines instead. The one thing you cannot do here is, I get kids who do this all the time, where they're like, okay, I'm going to draw lines and dots simultaneously. Well, one line means 2 electrons, and if I were to count this out, then I would say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, no, it's either lines or dots when you do them in a bond. Okay. Okay, I'm seeing on the live feed here about, nonpolar and polar and all that stuff. If you give me a minute, I'll go there, because the other thing I had to do with you tonight that was not on there was formula writing and naming. So when you have a bond, okay, a bond can either be ionic or a bond can be covalent. And bonds can be metallic, and that's a whole other story for a whole other day. I'm not going there right now. When you name a substance, you name it based on its bonding, because the name will tell you kind of what you have going on here. When you have something ionic, you have metals and nonmetals. Whereas when you have something covalent, you have 2 nonmetals. Each one of these has its own different naming system, and there's an overlap between the 2 with certain things, and we'll talk about that in a minute. When you name a compound, you need to make an executive decision. Do you have something ionic or do you have something covalent? If you have something ionic, you have to use the ionic naming system, which is what we call the stock system. And don't get me wrong, you can use stock system in some covalent scenarios, but I always teach stock is for ionic, whereas if you have something covalent, you can use the covalent naming system, which is the prefix system. And you can only use prefixes for something covalent because that is the the naming system. I'm just checking the live feed. I said I learned today that in the live stream throughout my year, my teacher always taught me no difference in electronegativity is non-polar and any difference is polar. I agree. I always teach my kids that non-polar is no difference. I don't even teach the numbers of 0.4 and 1.7 because there's too many exceptions to that rule. For your Regents exam purposes, no difference, non-polar. If there's any difference and it is covalent, it is polar. That's always how I teach it. The number 1.7 is like an arbitrary number that's like too many exceptions for that. If you are talking about polar, you're talking about something covalent. And the way for you to figure that out is if you have two nonmetals. I don't even teach 1.7 because there's too many exceptions to that rule. Okay, when you name something ionic, you start off and one more time. When you name something, the first thing you need to do is decide, is it ionic or is it covalent? Now, if it is ionic, you are looking for a metal and a nonmetal or some sort of polyatomic ion in here. The next executive decision you need to make is the metal in the compound weird or is the metal normal? And I'm going to explain what that means in a minute because this is something that is 100% me and how I teach it, and I guarantee your teacher will never, ever, ever use the word weird versus normal. Okay. I said, you're right. You can use the stock system for both ionic and covalent. I usually teach stock system is for ionic, and I teach that the prefix is for covalent, and I don't even tell my kids that they can use the stock system really for the covalents. I mean, I show them, but I pretty much drill into them that ionic and ionic goes with stock, whereas prefix goes with covalent, so that there's no confusion the day of the Regents exam. Okay, so when you name something that is ionic and you need to make the executive decision is something weird or normal. Well, when I refer to something as normal, I am talking about the oxidation number. So this lithium has a charge of +1. It's only one choice. Beryllium has one choice. Magnesium has one choice. Potassium has one choice. Rubidium has one choice. Those are all what I would consider normal because they only have one choice of oxidation number. As opposed to somebody like vanadium who's got 4 choices. Somebody like titanium who's got 3 choices. Chromium, manganese, they've got like crazy choices. This is the definition of weird. They have multiple positive oxidation numbers. That's what I mean by normal versus weird. Now, someone just said that stock numbers are only for transition metals. I agree with you that transition metals will get a stock number, but at the same time, not every transition metal needs a stock number. Somebody like tungsten is only +6, so he doesn't need a stocker number. Stock, not soccer. Stock number. Something like I can't say that one. Something like rubidium or scandium, well, they only have one choice of oxidation number, so I don't need a stock number for something like zinc because zinc only has one choice. So when I am referring to as a metal normal versus weird, I'm talking about the oxidation numbers. So if you were to have something like NaCl and you wanted to name this, well, you always name the metal first, and this would be sodium. You name the nonmetal, this would be chlorine, and what you do is you cross off the ending -ine and you add the ending -ide, which means bonded. This is sodium chloride because they are bonded together. Now, sodium and chlorine would be the atoms, and that would be like Mr. Sodium and Miss Chlorine. They are not married, but sodium chloride means bonded together. Somebody just texted in, there's many elements on the periodic table with multiple oxidation states. You are right. We are only talking about metals when we talk about stock numbers. And we are only talking about multiple positive oxidation numbers. So I know I wrote it here, multiple oxidation numbers. This has only one choice of a positive oxidation number. We are only talking about metals and the positive oxidation numbers when we talk about weird versus normal. Okay, so let's say you had something like barium oxide. Well, I would name this barium, I would name this oxygen. I would cross off the ending gin and I would add ide, and this would become barium oxide. I'm actually going to have to transition to a new piece of paper here. So we did barium oxide, we did sodium chloride. Let's name something like this guy. Okay. So I would name this first thing sodium, because that's what it is. And then we end up in this crazy situation where we have PO4. Now, PO4 is a polyatomic ion. And the deal with polyatomic ions is that we don't have to name them, because the beautiful thing is that they're already named for you. All you have to do is go to reference table E, and you would look it up, and you would say, well, where do I see this PO4 shebang? Oh, look, it's right here, and it's called phosphate. So I would just end up with this. I do not cross off the ending 8 because it already has an ending. It is already named for us. There's a whole entire naming system of polyatomic ions, which you do not need to know because they give you the reference table. It's already done for you. All right. So let's talk about weird metals. Let's say you had something like Fe2O3. So the first thing I'm going to do here is I am going to name iron. I am going to name oxygen, and I'm going to call it oxide. I am going to put a Roman numeral here. I'm sorry, a parenthesis here, because I need to determine, do I need a stock number? Now, if I go to the reference table and I look, iron has 2 different choices. It has a +2 and a +3 oxidation number. So the question becomes, well, what was this iron? Was it a +2 or was it a +3? I am going to determine that by reverse crisscrossing these numbers up. When iron bonded, it was a +3 charge. When oxygen bonded, it was a -2 charge. This is the crisscross method, but all you are doing is reversing the crisscross to figure out what you did. Now, in order to then put in your stock number, the stock number is the numerical value of the oxidation number for the metal. So this iron was a +3 charge, so I am going to put in the Roman numeral 3. This shall be named iron 3 oxide. Now what happens here is that kids are like, oh, so I'm going to name this iron 3, and they go to their reference table and they're like, but it's the second choice down. So then they call this iron 2 oxide because they're like, it's the second choice. You are giving me the numerical value of the oxidation number, which happens to be a +3 charge. Okay. As opposed to something like FeO, I'm going to name this again iron. I'm going to name this oxide. And then I'm going to say, well, I need a stock number. Now, if there's nothing written here, it is implied that this was +1 - 1 because that's what happened. You know, that's what it says here. We don't use them. But we need to do something really quick. We need to check the reference table. We want to check, can iron ever have a +1 charge? And if you look at your reference table, well, iron doesn't have a +1 charge. Iron's +2 and +3. Oxygen is never a -1 charge. Oxygen has to be a -2 charge. So we know oxygen has to be a -2 charge. This relationship right here is equal but opposite in sign. If oxygen has to be a -2, what would be equal but opposite to -2? +2. Which means that this iron had a +2 oxidation number. When it bonded, this becomes iron 2 oxide. Now, what happened here was that iron was +2 and oxygen was -2, which means the iron had to lose 2 electrons. The oxygen had to gain 2 electrons. When you crisscrossed this, you ended up with Fe2O2, which means you need 2 irons to satisfy 2 oxygens. Could you say that in a simpler way? Sure, we only need one iron to satisfy one oxygen, which means that you have reduced this. This is the reason why this is iron 2 oxide, because the iron lost 2 and the oxygen gained 2. Okay. So when we name something covalent, ionic, we are going to use the stock system. And the deal with the stock system is that if the metal is normal, we just name it. Slap on the ending "-ide", call it a day. If you are going to have a polyatomic ion, you don't change the ending. If the metal is weird, you are going to use a Roman numeral. And the Roman numeral is going to be the oxidation number. First name, last name, I'm going to bed at 11 also. I'm hearing you on that one because I'm really running out of steam super quickly. Okay, when you name something covalent, you're going to use the prefix system. And the deal with the prefix system is that you are going to name very similarly. You know you have something covalent if you have 2 nonmetals. You know if you have something covalent in a picture because you are sharing, because you see the lines. In a name, you would know if something is covalent because you would have prefixes in the name. Beautiful thing about prefixes is that if you were to name something covalent, it starts off the same way. We're going to name the first thing first, carbon. We name the second thing, oxide. And when I name something with prefixes, I leave 2 spaces out the front. Now, the rule here is that the last thing always, always, always needs a prefix, always, no matter what. This always gets a prefix. This first thing only needs a prefix if there's more than 1. So how many carbons are here? Oh, there's only 1. We don't need a prefix. Here there are 2 oxygens. This always needs a prefix, so this becomes carbon dioxide. If you had something like H2O, commonly known as water, and you were to name this according to fancy chemistry, this would be hydrogen first, oxygen, which is oxide, and then you put in your spaces. This is 2 hydrogen, so it only needs a prefix if there's more than 1, and there's 2, so it's dihydrogen. This is 1 oxygen. This always gets a prefix no matter what, so this becomes dihydrogen monoxide. That is prefixes. The tricky thing about prefixes is that you actually have to know them. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 hexa, yeah, 7 is hepta, 8 is octa, like Octomom, she had like 8 babies. 9 is nona, I think of like grandma, she's like nona, 90, great. And 10 is deca, like decade. Okay. I'm running out of steam. Okay, so I am going to pause for a minute and I'm going to leave you on the live stream. Take the last minute. Is there anything else you wanted me to address? I'm going to go for 13 more minutes and then I'm going to bed. First name, last name, I can't pour you a cup of sodium chloride unless it's in the aqueous form. Okay, Caitlin Hart said, can you go over cells really quickly? Are you talking about like biology cells, Caitlin Hart, or are you talking about like electrochemical cells? Is there a prefix for reference table for prefixes? No. Unfortunately, that's something you have to commit to memory. The prefixes as well as the Roman numerals, those are things that you need to know. What prefixes are in the reference table? I don't know any prefixes in the reference table. Yes, hydrogen fluoride would be hydrogen monochloride. Okay, yes, I figured she was talking about those type of cells. Okay. All right, I'm gonna do the trends of the periodic table really quick because I have the coolest trick ever, and then Sarah J and Fahim, I'll do electrochemical cells, and then we're moving on with life, and I'm going to bed. All right, so one of the things that I heard this year when kids were coming back from Regents review courses was there was a new trick out there, and it was called Amy. Is a really gross person. And this is for the different trends of the periodic table. This is atomic radius, ionization energy, metallic properties, and electronegativity. Now, the reason why Amy is such a gross person, and gross stands for group, and P stands for period, is because she picks her nose. And she picks her nose up and down and up and down. And then when she's done, she picks it down and up and down and up. And this tells you that for the atomic radius, as you go down a group, the atomic radius is getting bigger. As you go across a period, the atomic radius is getting smaller. For ionization energy, as you are going down a group, the ionization energy is decreasing. As you go across period, it is increasing. Metallic properties, you go down a group, it is increasing, and from left to right, it's decreasing. You get the idea. This is a cool trick, but at the same time, all you have to do is open up reference table, scary table S. I call it big and scary because it has so much freaking stuff on it. And all you have to do is look every single one of these up: atomic radius, ionization energy, electronegativity, metallic properties. That's just common sense because it's the structure of the periodic table. Okay, yeah, yes, Marissa, you can absolutely just look it up on the reference table. Okay. All right, this is it. I have 9 minutes to do voltaic cells, and then I'm calling it a night. A voltaic cell is a type of electrochemical cell. And when I think of voltaic, I think of like 9-volt batteries, because a voltaic cell is a battery. The purpose of a battery is to generate electricity. Now, the deal here is that electricity cannot be created, electricity cannot be destroyed. It has to be transferred from somewhere. So the chemicals that live inside of the battery are going to transfer their energy into electricity. Now, do you have to ask a battery to work? No. No. Batteries are just spontaneous, meaning that a battery is just going to run, it's going to work without you asking it to do so. So we're not going to put no. A battery is spontaneous, it's just going to work. Have you ever noticed on a battery there is an expiration date when you buy them? Because a battery is actually going to be discharging on the shelf and losing its energy over time. And you can actually buy batteries that are dead because they've been sitting on the shelf too long. So in a voltaic cell, you're going to take chemical energy and convert it into electricity. It is spontaneous, which means it's just going to work. A voltaic cell is going to have 2 sides. And the 2 sides are going to be filled with aqueous solutions. And these aqueous solutions are going to be some sort of salt solution, which means that they are going to have mobile ions in the solutions. Now, in each of these containers, there's going to be a strip of metal. And these strips of metal are called electrodes. And these electrodes are solid. Each strip of metal is connected to each other via a wire. And this is the general structure of a voltaic cell. There is something that is missing here, but I'm not ready to talk about that just yet. And if you know what you are talking about a salt bridge. I will put that in a minute because I'm not ready to address the salt bridge right yet. Now, if you were to cut this battery in half, if you were to look at it, there are two sides to a battery, and each of these batteries are called half cells. Now, in a half cell, you are going to have half reactions. So there's one half reaction, and you will find another half reaction on the other side. Let's call this electrode zinc, and let's call this electrode copper. Now, I'm going to tell you for the time being, and I'll explain to you how I knew that in a minute, that this zinc electrode is starting off at zinc atom, and it is becoming zinc +1. And I'm telling you that right now. I don't expect you to know that. Like, I will teach you how you would know that in a second. And what happens here is that the zinc atoms that are inside of this electrode are going to spontaneously dump their electrons into the wire. Now, this zinc is 0 charge, and it is a solid. And when this zinc +1 starts to lose its electrons, it is now able to dissolve into the solution. Now, if you were to assess this for oxidation numbers, this is becoming more positive, and more positive is Leo, losing electrons oxidation, which means I'm going to lose those electrons because they are exiting the reaction. Okay. Now, this electron goes into the wire, and it is now passed over to this side, and the electron arrives downtown to this side over here, and we're going to talk about what happens when this electron transitions across the wire in a minute. Now, on this side over here, this is half cell number 1. This is the half reaction that is happening, and this is Leo, which means losing electrons oxidation. In chemistry, this side where losing electrons is happening is called the anode. So the electrode where oxidation is happening is called the anode. And I know like every single one of you are blowing up the live stream right now. The acronym here is ANOX to help you remember that, as well as another way you could think of this is the anode is oxidation. It is where losing happens, and some teachers teach AOL, which means anode oxidation losing, which is another way of helping you remember this. So this is called the anode, which is the electrode, and this would be the oxidation half cell. Now, on this side, the electrons are coming in, and the electrons on this side are being accepted or gained by this electrode. And this electrode is called the cathode. And the cathode is where reduction is happening because these electrons are being gained. And again, red cat. Oh, you guys are blowing up the stream right now. And this is where the electrons are coming in, the electrode, which is the cathode. Now, what happens here is that the electrodes come in, and the copper has a 0 charge. Now, copper is neutral, and when copper sees these negative electrons, the copper's like, you're really not that attractive. I'm really not that interested. I'm neutral. I'm not really that interested. However, there are copper ions hanging out in this solution, and this copper ion is +1, and it sees this negative electron, and it's like, oh my god, you are like the most attractive electron I've ever seen. I'm +1, you're a -1. This is like match made in chemistry heaven. When the electrons leave the anode, they pass through the wire, and they arrive downtown at what I call Cathode Town's bus stop. The electrons are not attracted to the copper atoms, but they are attracted to the copper ions in the solution, and those electrons are picked up by the copper +1, and they are becoming copper 0. Now, other things you need to be aware of here. The anode is oxidation and it's losing, and when you lose, you become smaller. This electrode over time is becoming smaller because the atoms are becoming ions in the on the anode side, and they are being dissolved into the solution. So this electrode gets smaller over time because each time one of the electrons are put in the wire, an atom becomes an ion and it gets dissolved into the solution. Is this zinc +1 or is this zinc +2? Because that's actually really embarrassing if this has been zinc +2 the entire time. Sorry, it's like 11 o'clock at night. I'm really tired. Of course I can't find my periodic table anywhere. Isn't that embarrassing? This is not zinc +1, this is zinc +2, which means this is 2 electrons, which means it's losing 2 electrons. This has to gain 2 electrons. Let's call this copper +2 because that works. Copper is not even +1. What the hell am I doing? Okay, let's fix that. I'm really sorry. Like I said, it's been really, really late. Okay. So on this side, we are going to talk about the cathode, and the cathode, the mass on this side is going to get larger. And the reason why it's getting larger is because the copper ions, which were once dissolved, are becoming copper atoms here. And the copper atoms are solid, and they get stuck to the electrode. Okay, I'm just going to talk about the salt bridge, and then I'm calling it a night because it's over. Now what happens here is that over time, when the electrons get put into the wire, losing electrons is positive. So there is a positive charge that starts to build up on this side. When the electrons are being passed over, when they are gained on this side, there's a negative charge that starts to build. Now, this is the biggest misunderstanding and the hardest thing that kids have a time with. So this is why I want to finish on this note and then call it a night, because I'm done. Burnt out. When the electrons get put into the wire, this positive charge starts to build up. Now, electrons are negative. They go up into the wire, and when they're put into the wire, they take a look back at where they came from, and they were like, oh, this place is really positive. If you put a negative next to a positive, they are physically attracted to each other. So these electrons go in the wire, and they're like, why am I leaving? This place is awesome. I want to stay forever because it's positive. And just humor me for a minute. If these electrons actually pass down the wire, and the electrons get downtown to cathode town, well, this is a negative sign, and the electrons get here and they're like, what the heck? This is supposed to be the cathode. We want to stay, but I'm negative, and this place is negative, and this is like really gross and disgusting. I don't want to stay here. If the electrons do not pass through the wire, the battery stops working immediately. And because of these charges, the battery will stop running unless we fix this problem. So we are going to put in something called a salt bridge. And the salt bridge is going to contain an ionic salt, and basically that's just a keyword for ions. And the most popular thing to put in a salt bridge is something like NaNO3. And the reason why you would put something like NaNO3 in is because if you take a peek at reference table F, Na is in group 1, and this is soluble, which means it's aqueous. And if it's not aqueous, it would be an exception, which makes it a solid. Now, when I read reference table F, I read it up, down, over. So I start with group 1, and I'm like, oh, look, group 1 is always aqueous, except there's nothing in the box because it's never an exception. It is always aqueous, except never. At the same time, you have nitrate, which is always aqueous, except, oh, look, there's nothing in the exceptions because it's always aqueous, except never. If you have something that is always aqueous except never, then you never run the risk of them interacting with other things in here and forming a solid and maybe chemically reacting with things that you're just not supposed to be reacting with. So sodium is +1 and nitrate is -1. So what we do here is this positive cannot stay here. So what we will do is we will take the positive and it will be put into the salt bridge. Now, I don't just want to take the positive and put it in. I actually want to take a negative and push it out so that this is no longer positive. We need a different color marker to hit this bad boy home. So this is no longer positive. It is now negative. When the negative electrons go in the wire, they turn back around and they're like, ew, it's negative. Gross, repel across the wire. So the electrons like shimmy their way down and they arrive downtown to cathode town. Now, it's not okay just to fix this side. We need to fix this place and make it like super attractive like Disney. Well, not anymore because of the alligators, but like Disney, and make this place like super crazy attractive so the electrons like want to stay forever. So I need to get rid of this negative. We're going to put the negative into the salt bridge. And I don't just want to make this negative. I want to make this place super attractive. And I'm going to pull out a positive. So we stick the negative into the salt bridge and we pull the positive out. And now the electrons arrive downtown to cathode town. They're like, awesome, this place is positive. We're staying forever. In order for you to have a functional voltaic cell, you need a salt bridge to allow the migration of ions. And the purpose of the salt bridge and the migration of ions is to prevent the polarization or the buildup of residual charges that are not supposed to be there. Now, ladies and gentlemen, I'm done. I'm calling it a night. I hope this was helpful for you because it was awesome for me in a not barium chloride kind of way, but actually in a good way. And it's been a real pleasure. You have access to me through Remind. I'm calling it a night. You have access to me, I guess, on the video chats. And have a wonderful night. Good luck. And good luck. Okay, I just got to figure out how to turn this thing off. I'm going to have to call my husband in. Wait, and I'm going to do it. Craig? Craig.